Up until now, we have worked with different problems of the binomial theorem for an expression given by having the form x plus a raised to the power of n equals to summation r going from 0 to n ncr times the first term, which is x, raised to the power of n minus r times the second term, which is a, raised to the power of r. So here n was considered to be a positive index, positive natural number. So that was a requirement, and we have done lots of problems based on this particular format. So in today's lecture, we're going to talk about the binomial theorem for any index. So here n could be a negative number or it could be a fractional number. So let us begin. So this lecture is going to involve a little bit of differential calculus. If you have taken a course on the differential calculus, then this will be pretty much helpful for you. Otherwise, you can just have a look at it and wait till the answer. Okay, so let us begin by considering a polynomial function f of x. So a standard polynomial function with n terms is given by a0 plus a1x plus a2 x squared plus a3 x cubed all the way up to the nth term, which is simply an x raised to the power n. So this is a nth order polynomial function. Now what we're going to do, we are going to find the value of this function at x equals to 0. So that would give us f of 0. So f of x calculated at x equals to 0 will give us the first term, and you can see the rest of the term will be 0 because all of them has the term involving x or the higher powers of x. So as they're multiplied to it, so the terms will simply cancel out. Now what we do, now we find out the first derivative of the function fx. So that should give us f dash of x is equals to, the first term is a constant term, so the derivative will be 0. So we're left with the second term, which will give us a1 times the derivative of x is simply 1 plus a2 times derivative of x squared will give us twice of x plus a3, the derivative of x cubed is going to give us thrice of x squared all the way up to the nth term, which is going to give us an times n x raised to the power n minus 1. So now that we have the first derivative of fx, so we're going to calculate the value of this derivative at x equals to 0, which was going to be simply equals to a1. So this is the value of our derivative, the first derivative, and its value is a1. Now what we can do, well, we'll try to find out the second derivative of the function. So this is going to be f double prime x, which is equals to, so the first term is a1 times 1, which is simply a1, it's a constant term, so it will be 0. Then we move on to the second term. So we have a2 times derivative of twice x will be simply 2 plus a3 times the derivative of thrice x squared, and that will be 6x plus dot dot dot. If you check it out, so we have a4. Here I have not mentioned yet the fourth term in f prime of x is 4x cubed. So the derivative of 4x cubed will be simply 12x squared plus all the way up to the nth term, which is simply going to be en times n minus 1 times x raised to the power n minus of 1. So now what we're going to do, we're going to find the value of f double prime of x calculated at 0. So that is going to give us only the first term, which will be simply twice of a2. Next, we're going to calculate the triple derivative of function fx. So the triple derivative of fx is going to be f triple prime x equals to, we have the first term as 2 times a2, so that will be 0. So we move on to the second term. So we have a3 times the derivative of 6x is going to be 6, plus a4 times derivative of 12x squared is going to be 24x, plus all the way up to the final term, which is the nth term, and that will be simply an times n minus 1. So this is not n minus 1, this is n minus 2. So n minus 1 times n minus 2 times x raised to the power n minus 3. Now we calculate the value of f triple prime x at x equals to 0. So that gives us 6 of a3. So I'm going to list out the value of f prime of 4. So f prime 4 prime, that means the fourth derivative of function x calculated at 0, is going to be equals to 24a4. And the fifth derivative of the function calculated at x equals to 0 is going to be equals to 120a5. So what I'm going to do, I'm going to list all the values starting from f prime of 1. So let's do that. So we have fx, so we have f of 0 equals to a0. Then we have f of 1, which is equals to a of 1. F prime of 1. Make a mistake here. This is f prime calculated at x equals to 0. That gives us the a1. We have f double prime 0 equals to twice a2. F triple prime 0 gave us 6a3, and f, the fourth derivative of f calculated at x equals to 0, gave us 24a4. Now what we can do, a0 will keep it as the way it is, such that now we have a of 0 is equals to f of 0. What we're going to do is we're going to write the coefficient, all the coefficient in terms of the function and its derivatives. So here a1 will be equals to f prime of 0 divided by 1. So this will become evident in a moment. So this is divided by 1, which can be written as f prime of 0 divided by 1 factorial. 1 factorial is 1. Now a of 2 will be equals to f double prime 0 divided by 2, and that value is equals to f double prime 0 divided by 2 factorial, which implies a of 3 will be equals to f triple prime 0 divided by 6, which is simply equals to f triple prime 0 divided by 6 can be rewritten as 3 factorial. And for a4 we have f, the fourth derivative of f calculated at x equals to 0 divided by 24, which is 4 factorial. And if we continue the trend, we will have f of will have a5 will have a5 is equals to the fifth derivative of function f calculated at x equals to 0 divided by 5 factorial all the way up to the nth term, which will be simply equals to the nth derivative of function f calculated at x equals to 0 divided by n factorial. So the reason why I have written it in this particular format is what we're going to do. We are going to replace all the constant coefficients in our polynomial function of nth order by these new values in terms of the derivative. So let's do that. So we had f of x equals to a sub 0 plus a1 times x plus a2 times x plus a3 times a2 times x squared plus a3 times x cubed plus all the way up to the nth term, which was an x raised to the power of n. Now what we're going to do, we're going to replace this by the respective function and the derivative values. So we found out that this one was equals to f of 0 plus a sub 1 was f, the first derivative of function calculated at 0 divided by 1 factorial times x. A sub 2 was the second derivative of function fx calculated at x equals to 0 divided by 2 factorial times x squared. And for a3 we have the third derivative of function f calculated at x equals to 0 divided by 3 factorial times x cubed all the way up to the nth term, which is the nth derivative of the function fx calculated at x equals to 0 divided by n factorial times x raised to the power of n. So this is our function fx, which was an nth order polynomial function, and now we have written in terms of a Maclaurin series. In a more condensed form, the above Maclaurin series can be written as fx is equals to summation k going from 0 to n. We have f k dk derivative calculated at 0 divided by k factorial times x raised to the power of k. So this is a Maclaurin series for a finite number of terms, and for n number of terms. If we are to extend it to infinite number of terms, then we will have f of x is equals to k going from 0 to infinity f the kth derivative calculated at 0 divided by k factorial times x raised to the power k. So this is for infinite terms, infinite number of terms, and this will be the finite number of terms. Now this was an introduction to Maclaurin series, or how to use the Maclaurin series to write a given polynomial function of nth order. We started with this nth order polynomial function and how it could be expressed with the help of a Maclaurin series. Then we extended it to infinite number of terms. So this is what we're going to use. Now that we're familiar with this Maclaurin series, let's move on to the more general definition of the binomial theorem. So let us calculate the value of the function fx at 0, at x equals to 0. So that would give us simply 1. Now we find out the derivative of the function, first derivative will be equals to n times 1 plus x raised to the power of n minus 1. Then we find out the value of the derivative at x equals to 0. So that would be simply equals to n times 1 plus 0, which is 1, and 1 raised to the power of n minus 1 would give us only 1. Then we find out the second derivative. So second derivative will be equals to n times n minus 1 times x raised to the power of n minus 2, such that the second derivative calculated at x equals to 0 would be simply equals to n times n minus 1. So we continue, and we reach the nth derivative of the function x. So that should be of the form n minus 1, n minus 2, all the way up to n minus r minus 1. We didn't stop at r here because we have started from n minus 0. So that's why we have to terminate at r minus 1. So that means we are at the rth term here. Not rth term, this is r minus, so yeah, that is the rth term, such that f and the derivative calculated at 0 would be simply equals to, and wait, so we have x raised to the power n minus r, such that the nth derivative of function f calculated at 0 will give us n minus 1 times n minus 2 all the way up to n minus r plus 1. So we have all the values of fx as well as the successive derivatives calculated at x equals to 0. So what we're going to do now, we're going to use our Maclaurin series, which says that given the expression fx, which is 1 plus x raised to the power of n, so that will be equals to summation r goes from 0 to infinity f the nth derivative of function f calculated at 0 divided by n it will be r factorial times x raised to the power r, and this will be equals to summation r equals to 0 going to infinity. So we replace the value of the nth derivative of f, which is simply n times n minus 1 times n minus 2 all the way up to n minus r plus 1 divided by r factorial times x raised to the power of r. Now what we're going to do, we're going to multiply and divide. So let's write it down. 1 plus x raised to the power of n is equals to summation r going from 0 to infinity n times n minus 1 times n minus 2 the way up to n minus r plus 1. Now we're going to multiply with some extra terms, so that would be n minus r times n minus r minus 1 all the way up to 3, 2 and 1, and divide by the same number of terms. So that will be r factorial times n minus r times n minus r minus 1 all the way up to 1 times whole thing times x raised to the power of r. So this is now can be, so we have summation r going from 0 to infinity. So the terms in the numerator is simply n factorial. That's the expansion of the factorial divided by r factorial times, so n minus r, it's the next term, which is one unit less than the previous term, and so forth. It goes up to 1. So this can be combined and written as n minus r factorial times x raised to the power of r, which is simply equals to summation r goes from 0 to infinity. So this is the formula for NCR times x raised to the power of r. So with the help of our Maclaurin series, we were able to find out the expansion of 1 plus x raised to the power of n, which is simply summation r goes from 0 to infinity NCR x raised to the power of r. Now we have to look at the convergence of this particular series. So let's look at it by doing a ratio test. So here we have the nth term. So what is our nth term? So our nth term, so it's actually AR, which is equals to NCR x raised to the power r. Now we take the next one, which is a plus r plus 1, the r plus 1 term, and that will be NCR plus 1 times x raised to the power of r plus 1. Now we're going to divide AR plus 1 by AR, which should give us NCR plus 1 divided by NCR times x raised to the power r plus 1 divided by x raised to the power of r. Now we're going to expand NCR plus 1, which is simply going to be n factorial divided by r plus 1 factorial times n minus r minus 1 factorial divided by NCR, which will be simply n factorial over r factorial times n minus r factorial times x raised to the power r plus 1 can be rewritten as x to the power r times x divided by x to the power r. Now what we can do, we can factor out n factorial from both the numerator and the denominator, as well as x raised to the power of r from both the numerator and the denominator, which will leave us with a r plus 1 divided by a of r, which is equals to, we have r factorial in the numerator and n minus r factorial, that can be written as n minus r times n minus r minus 1 factorial, so that we can factor it out from the term, from the value present in the denominator. R plus 1 factorial can be written as r plus 1 times r factorial times n minus r minus 1 factorial. So we cancel out all the common terms from the numerator and the denominator, and that leaves us with times the x is also there. So we have n minus r divided by r plus 1 times x. Now we have to do, now we have already divided, so we're going to do the ratio test, which says that limit r going to infinity, the absolute value of a r plus 1 over a r is going to be equals to limit r goes to infinity times n minus r over r plus 1 times x. So we're going to divide both the numerator and denominator by r. So we have limit r going to infinity. So we have n over r minus of 1 divided by 1 plus 1 over r times x. So let's take the x out of it. So when we calculate the limit, so we'll have n over infinity minus 1, so that leaves us with negative 1, the absolute value of negative 1 divided by 1 times modulus of x, so which is simply mod of x. So we have limit r going to infinity er plus 1 divided by er is mod of x. Now we know that the series is going to converge when mod of x is lesser than 1. Then only it's going to converge. Otherwise diverges for mod of x greater than 1. So we have the radius of convergence, which is the absolute value of x less than 1. So now we come to the final definition of the binomial theorem, which states that for any rational number n, for any rational number n and some real x and some real value x, such that the absolute value of x is less than 1, we have 1 plus x raised to the power of n is equals to summation r going from 0 to infinity ncr x raised to the power of r. So this is the definition of binomial theorem for any given index x. Now here's a remark that I would like to point out. So the value of x, the absolute value of x must be less than 1 if our index n is a rational number. Otherwise, it's unnecessary to consider this particular condition if n is a positive integer. Now there are a few more remarks that I'd like to make before concluding this lecture. Now we have given that this is the standard form of the binomial theorem for any index. Now what if we have an expression given by x plus a raised to the power of n? So what we're going to do, we're going to rewrite it as a plus x raised to the power of n, and then we are going to factor out a, which leaves us with e raised to the power of n plus x over a raised to the power of n, such that this will be equals to an summation r going from 0 to infinity ncr x over a raised to the power r, and the absolute value of x over a must be less than 1, or you can say the absolute value of x must be less than the absolute value of a. So this is how we can express any given binomial expression for some rational integer n in this particular format. So in the next lecture, we're going to work on problems based on this particular theorem, and that will solidify your concept. See you in the next lecture.